Welcome to the Rare Earth Exchanges podcast, where power, politics, and the world's most coveted materials collide. Rare earth elements power the backbone of tomorrow's most critical technologies. With China dominating global production, the U.S. and its allies must align strategically to ensure a stable future. This urgency prompted tech entrepreneurs Daniel O'Connor and Dustin Olsen to launch Rare Earth Exchanges, a news and insight platform built to equip stakeholders and decision makers with the tools and intelligence needed to reduce dependency and build prosperous resilience. Let's get into it.
Hey everyone, welcome to the Rare Earth Exchanges podcast. You're joined by me, my host, Daniel, and our special guest, Ali Emadi, who is the founder and CEO of Enidime, and they're a company pioneering magnet-free motor technology that aims to reduce the world's dependence on rare earth magnets. So, Ali, welcome to the show. We are so thrilled to have you here and to talk about this innovative technology and possibly the solution to our problem. So, could you just give us a quick intro about your background and Enidime?
Thank you, Dustin, for having me. I have two main hats. One is I'm a university professor and shareholder at McMaster Automotive Resource Center, McMaster University in Hamilton, Ontario, Canada. And also I'm the founder and the CEO of Enedym. And Enedym is a spin-off company, a startup company of McMaster University. Before coming to Canada, I was at Illinois Institute of Technology in Chicago. From 2000 to 2011, I was a professor and shareholder there and built the automotive power electronics and motors and motor drives program there at Illinois Tech in Chicago. And in 2011, I was recruited by Canadian government and McMaster University to come to Canada as the Canada Excellence Research Chair focused on electric motors and automotive powertrains. And since then, I have been at McMaster University.
That's awesome. So when you look back at founding Enidime, what problem were you trying to solve in the electric motor industry specifically? What drew you there?
So the electric motor industry is a massive, massive industry. There are 10, 15 million motors manufactured a day worldwide. This is just gigantic. And about half of electric power from the electrical grids around the world, it's used for electric motors. And electric motors are the beating hearts of anything that moves with electric power, whether it's a two-wheeler or an electric car, truck. The thing that drives the vehicle, an electric or a hybrid one, is the electric motor. Majority of electric propulsion motors use permanent magnets and they use rare earth metals. I remember when I was being recruited to come to Canada in 2011, at that time, folks might remember there was the issue between China and Japan on rare earth metals. And the price of dysprosium and neodymium went up. And I remember back then, and I knew such problems would come again. And we are just too dependent on rare earth metals for electric motors. So back then, we decided, and I had a lot of funding from Canadian government and McMaster University, and we set our goal to solve this problem once and for all for electric motors. There are applications that you might not be able to remove, but for electric motors, definitely you could do that. So back to 2011, we started the program at McMaster University at the tech park of the university, McMaster Innovation Park, where our facilities are located. And since then, we spent millions of dollars, tens of PhD, masters, thesis students, researchers, engineers, postdocs, and we went really deep. We focused on switched reluctance motors or SRMs. Such motors have been around for decades, but they have had acoustic noise problem. They have been noisy. And in terms of torque density and power density, they were not able to compete with permanent magnet motors. So We said, okay, we need to solve those problems. We put our head down. We are, I believe, one of the largest university programs in the world in electric motors. We are one of the best also. And it's not me saying it, actually Google Scholar says that. So we focused for 7-8 years, just technical, go deep, try to develop technologies that eliminate the need for rare earth metals completely from electric motors by focusing on switch reluctance motors. And then in 2018, 7-8 years later, we formed Enidime. And Enidime stands for Energy Paradigm Combined. That's Enidime as a university, a startup company. And the IP from my university lab went to Enidime. So Enidime owns, at this point, 59 patents and 20 some pending patents, and the IP were moved from, we took the IP from the university to the company. The university owns a portion of the company, and since then we have been trying to commercialize our motor technologies.
That's fascinating. So just for the simple people like myself, could you just do a brief explanation of how a rare earth free, magnet free motor works?
Yeah, when you have an electric motor, think about a typical electric propulsion motor. You have electrical steel, laminations, you do a stamping, you put them together, you make the motor cores, a stator and the rotor cores. And then for the stator, you have windings, either copper or aluminum. Now, permanent magnet motors, they have permanent magnet pieces, most of them with rare earth metals and heavy rare earth metals inserted in them or on their surface. And it's very interesting that depending on the application, sometimes up to 40%, up to 40 to 50% of the cost of the motor is for those permanent magnet pieces. This is just, too much, right? For a smaller motor application, it might be 20, 30%. For a bigger one, could be 40% or above. So you have them on the rotor. And then advanced motor drives, that's the electromagnetic piece, that's the electromechanical piece. And then you have electronics, power electronics to drive the motor. And then you have control and software to control your solid state semiconductor switches to drive the motor. Now, what we have done, we focus on switch reluctance motors that our rotor for the motor is simple, just electrical state, no permanent magnets whatsoever, no windings, and the stator has a simple stator core electrical steel, and we use copper for most of our designs. We can use aluminum too, and the color of Enidime is copper, Enidime branding with the motor. And so our motors, switch reluctance motors, are the simplest, lowest cost motors from the hardware you could have. The complexity has been shifted to software and control. So our motors are amazingly simple. The electronics is kind of the same with permanent magnet motors or induction motors or other motors, but the software of our motors are a lot more complicated, and we have really complex software. Now, such motors, switch reluctance motors, inherently, they have acoustic noise problems. They are noisy. And it's interesting, up to like 5-6 years ago, my whole adult life after I got my PhD in 2000 has been kind of on motors, powertrains. 5-6 years ago, we would talk about switch reluctance motors. People throw shoes, tomatoes, eggs, and they would say these motors are noisy. And, OEMs have told me that they designed switch reluctance motors and like 20 some years ago, and their ears were still hurting from the noise. And I'm saying, are you listening to yourself? That was 20 some years ago. If there was a baby back then, the baby is graduating from college at this point, and don't you think somebody smarter showed up or solved this problem? So what we did, we went to deep science of it. We solve for those acoustic noise problems, torque repel problems. And that's the reason our software and control, they are a lot more complicated than a typical motor. But when you do manufacturing, once you do the software, it doesn't matter. We use the same microcontrollers or microprocessors or digital signal processors, so the hardware doesn't change. It's just the coding we have developed it.
So I had a question. Can you both hear me okay? Thanks, Ali. One of the critiques we hear and read out there is that while there are some breakthroughs with rare earth free, base magnet and motors, first of all, they're not quite on par with the rare earth based approach, number one. Number two, that the design of these different types of lines of products would need to change, and that would be a costly intervention and a combination of technology maturity levels, entrenched investment, and current infrastructure makes it to where there's probably going to be an adoption curve that may take time and may be focused on maybe low-hanging fruit. Could you talk about that and where we're at in the life cycle of this new technology?
So at Enidime, we have two groups of IP. One is the motor itself, technologies on the motor, electronics, and control and software. But another group is digitization. We have developed a very comprehensive software platform that is multi-domain, multi-physics, multi-objective, AI-enabled design platform that we design social reluctance motors at a fraction of time and cost than others. So that allows us to do really good optimization. And at the end of the day, it's a science and engineering problem, right? And with optimization to achieve the performances required for different applications. Now, Enidime has been doing motors from, less than 2-3 kilowatts for two-wheelers, scooters, to 3 to 10 kilowatts for like scooters, motors, and then 10 to 20, and then 20 to 40, 50 kilowatts, and then up to 200 and more kilowatts for propulsion. Every applications that we have done, we have benchmarked against existing permanent magnet motors. In every single of them, so far, we have been able to meet or exceed the performance requirements of permanent magnet motors. Now, I would say one issue is the lot of existing permanent magnet motors out there are not optimized really well. And that's one reason that if we design our switch reluctance motor, no permanent magnets, we can beat them. Now, a fair question is, if my team with the same capabilities design the permanent magnet and my team with same capability design a switch reluctance motor, can we beat permanent magnet in terms of power density and things like that? And that's, in terms of efficiency, especially if it's a wide range over a speed range efficiency, we can beat permanent magnet and meet the requirements. In terms of cost, we are definitely far lower cost, but in terms of power density, no. So our motor will be, if again, we design and optimize. Luckily for us, most of the rest of the world, they are not that optimized. By the way, at the university, we have multiple large projects with OEMs. We reduce rare earth content. So we have permanent magnets that we reduce them, optimize, and so on. Now, if we design both permanent magnet switch reluctance motors, since we don't have permanent magnets, our motor will be slightly heavier. And I'm talking about like half a pound heavier for a car, right? The motor would be 40% or so lower cost, but it would be slightly heavier than permanent magnets. We have a slightly more electrical steel and copper. The cost is much lower, but the motor is heavier slightly. Now, if you are an automotive OEM, this is the thing that gets me. Up to 4 years ago, people would say, oh, your motor doesn't meet this power density of these very expensive permanent magnet motors. And I say, do you really care if your motor is half a pound heavier? Before dinner, after dinner, I myself like 2-3 at least pounds heavier driving that car. It's like, who cares if the motor is half a pound heavier or so? So that would be the trade-off.
But what is, let's look at the sensitivities of the current. Well, let's put it another way. What would be the sweet spot to start replacing heavy rare earth elements, heavy rare earth magnets with these non-heavy rare earth motors, what would be the most easy transition based on design of the underlying product set that you need to replace? Like where to start in your business plan?
So I answer this question with exactly what we are doing right now. So it's what we are doing. The market that is very attractive is two-wheelers, light electric vehicles and micromobility. So, and I give you the example. So we are working with some of the largest two-wheeler OEMs in the world, and think about they have a permanent magnet motor for their two-wheeler, a scooter or motorcycle. What we have done, you just remove that. That permanent magnet motor is a motor and separate power electronics and control somewhere else inside the vehicle. So we remove the permanent magnet motor, we put our motor there. Same connection, same size, exactly same size. And the interesting part is our motor is integrated, motor and inverter and gearbox together. So actually it makes it easier for the OEM. So we are doing that. And why that's interesting, because that's a market that is really sensitive to cost. So for them, a 20-30% lower cost is awesome. And if you don't need to be dependent on China, for example, for India, that's a very good market, and the volumes are very high for those applications. So we are focused on that. Another sweet spot for us is on industrial vehicles. We have a really good collaboration with Toyota Tsusho Canada, and is on luggage tuggers. So Toyota has, for example, luggage tuggers. You go to airports, you see a lot of those luggage tuggers and tow tractors in plants, factories, and so on. A lot of them are actually diesel engine tow tractors. And we have developed motors that are like 40 to 60 kilowatt. We have a bigger one, 120 kilowatt, that converts the powertrain from diesel to electric. Now, those are, okay, the volumes there, our plans is to go to like 10,000 units a year, is not automotive, hundreds of thousands, but the margins are a lot higher than automotive. And you have a lot less resistance to penetrate the market than automotive. And for a small company like us, a startup that is growing, the margins would allow us to even be profitable at hundreds of motors making, and then lower thousands. We don't need to go to like mass volume to make them profitable for us. The other thing is that approach actually works for automotive, but automotive industry is general, really conservative. Convincing a major OEM to go to a battery electric vehicle with our motor before they see, a bunch of other applications, that's a barrier in their mind. But the approach is you remove the permanent magnet motors, you put our motor in there, same thing, right? And we are making great progress with several OEMs. We'll be announcing, hopefully within 12 months or so, some good programs for automotive, but automotive is longer term.
That makes sense. And again, the risk-averse nature of industry, I could see, is a challenge, even in the sweet spot scenarios. So you have to find organizations that are really thinking about this and to have a culture of an open inquiry and investigation for pilots for this transition. Does that make sense? Is that an approach you all are taking?
Yes, that makes sense. We have faced, several OEMs over the past 20-25 years. They tried to make switch reluctance motors work. Some of the big tier ones tried that too. Everyone, to the best of my knowledge, failed, couldn't solve the noise problem and torque repel problems and power density problem. So when they see the solution, so we have, you show them the motors, we have literally hundreds of papers, journal and conference papers, peer-reviewed on these topics. We have books on this. But again, those things are not as important as them seeing the unit. So they see the units, they test the unit, then they say, we need to see it in a vehicle. So we have, very interestingly, at the university, we are part of the EcoCar competition. GM leads is a Cadillac Lyric platform that we have. We have an Enidime switch reluctance motor in there, and is performing really well. And that has changed the equation, frankly, that these motors they are not noisy, they perform really well, and they are actually more reliable. So the OEM folks, they need to get over this noise problem in their minds. Once they are over it, they see a ton of other benefits for such motors.
Is there any, and this is really helpful, I want to get a little bit into your company as well, but is there any in your go-to-market? So there's a lot of research. Do you have any customers in production with the alternative approach, or are we still in the early pilot sort of stages where we're test driving before we go commercialized?
So there are, when you look at, let me answer it from a professorial point of view as an academic answer, and then Enidime. So if you look at the permanent magnet motors and the competition, there are other motors like induction motors, like wound rotor motors, ESMs, freight magnets, synchronous reluctance motors, and so on. Some of them are actually in production, and many of them, they have cost issues, other challenges, and not being able to completely beat permanent magnets. Our focus is on switch reluctance motors, and our motors, we are not in volume production right now with any OEMs, but we are very close. And from two-wheelers to industrial vehicles and to automotive, and the time frame, I would say, would be 3 to 5 years, and I'm being conservative here, for volume production, some of those by us, by our factories that we are planning right now. So our capacity right now is lower thousands in Hamilton, Ontario.
That's helpful. But again, it's a very important topic because, again, as we have reported on the Rare Earth Exchanges platform, media and podcast, is that part of the West, United States, Canada, transcending this crisis will be to find replacement products, to innovate out of this crisis, right? Or set of crises, right? So what you're doing is very important, and investors that are interested in this topic should understand the landscape. There are other non-rare earth magnet makers too, right? Like the Neuron magnetics and what have you. But what you're doing is very important. What's the size? I mean, like, what's the forecast? I mean, if you look at your company and what is conservatively, how many different companies? So let's take a step back. So there's, on any given day, how many electric motors being produced?
So Enidime has about 40 people, and we have at this point, and we have for the technical stuff, it goes back to 14 years ago. We took our time, developed the technology, and we have been focused mostly on strategic partnerships and ecosystem. One of our strategic investors is JFE Soji, and JFE is one of the best electrical steel. JFE Steel is one of the best electrical steel suppliers in the world, and JFE Soji does motor stamping, motor core. So we have an amazing partnership with them. They invested in us. We have an amazing partnership with Marcelli for motor windings, and same thing for PCB, printed circuit board assembly, things like that with others. So we have been building an ecosystem. So if you look at the tagline of Enidime, is changing how the world moves together. The word together is really important for us. And so far, we have not focused on getting a lot of financial investment and going a lot faster. And frankly, that's the thing we are debating within Enidime and our board, that from investors' point of view, or let's say from US point of view, North America or West, there are spending, $1 billion to do mining and processing, versus we are a lot less than that investment needed. And it's like a lucky situation that we just did the homework until this point. So a much smaller investment would allow us to go a lot faster. So we are actually debating that we should perhaps accept investment and go a lot faster. Now, if we go a lot faster, we have a plan to do GigaFarm. Farm stands for Facility for Advanced Rapid Manufacturing. That's the current facility we have in Hamilton, Ontario. GigaFarm would have a capacity of 250,000 motors and inverters a year. So we are now going through, should we accelerate that. Instead of the next 5-6 years, we do it sooner. We will have a giga farm in India, focus on two, and we will have a giga farm in US. But the time frame so far for us, 5 to 7 years from now, because we wanted to go really conservative, and with our partners, strategic partners, we are going through this debate that maybe we need to accelerate and go a lot faster. So with proper investment and funding, we can go a lot faster actually, because we have solved the manufacturing problems, technical problems, those things.
I have some other questions, but Dustin, please jump in. I don't want to monopolize all the time.
I had a question. It was kind of prompted earlier with the comment you made about the reliability of these motors. I would imagine a common misconception when thinking about permanent magnet motors, they would probably last forever because of that compared to something without them. So what's the lifespan of your motor compared to a permanent magnet motor? A follow-on question to that I was thinking of as well is, how is it efficient with the battery? Does it drain it faster? Does it conserve battery more? Because, I mean, range anxiety is a thing. Anyway, tell me what you think.
So let me take your second question first. So regarding batteries, no difference. Our efficiency is the same. And one thing some companies say, peak efficiency. I think peak efficiency doesn't matter much as long as the average efficiency is high. So you need to be better in terms of average efficiency. And in terms of average efficiency, everywhere we have gone so far, we are meeting and exceeding the requirements of the OEM. So from that point of view, it doesn't have any impact on the battery or range. Now, we have a lot of technologies to make the current smoother, so the battery would not deal with harmonics, things like that. So you extend the life of the battery. That's a secondary advantage of the things we do. Now, to your first question, this is such an important thing. Permanent magnet motors, they need to be pampered. This is something I heard from Professor Fahimi of UT, University of Texas, Dallas. And you need to be nice to them. What does that mean? That means temperature goes up, they don't like it. The permanent magnets get demagnetized. You go off-road or the roads are not as smooth, you shake the motor, the permanent magnets get demagnetized. So the motor get aged, they get demagnetized. Over the years, the permanent magnets, they lose their magnetization. You go higher speed motors, permanent magnets, the back EMF is so high, you actually inject the current to cancel permanent magnets. This is called field weakening. And that over time, could demagnetize the motors. So permanent magnet motors, and a lot of people don't realize that, you really need to be nice to them. Keep the temperature, thermal management, all of that. Switch reluctance motors don't have permanent magnets. Temperature goes up on the rotor, fine. The electrical still, they can take it, right? So switch reluctance motors are really reliable and rugged compared to other motors. And you can go higher speed. By the way, if you let me go higher speed, and we are planning for something more than 30,000 RPM for traction motor, right? Permanent magnets, good luck. You cannot do that easily, right? So when the speed goes up, switch reluctance motors shine. And the motor gets smaller, actually, more power dense. The other advantage of switch reluctance motor that we have seen from defense applications and also industrial applications, if you have a permanent magnet, something goes wrong with your vehicle, if you don't have a clutch, you cannot tow it. Because if the vehicle is running, the motor is running, it generates power. It could damage the system. Our motors doesn't matter. So think about the tow tractor. If something goes wrong, you have permanent magnets, you need to bring a flatbed truck. With our motors, no need for that, right? The last point I want to make, our motors, switch reluctance motors, are inherently fault tolerant. Imagine you have a 3-phase motor. If one phase fails, permanent magnet motors, you cannot do anything. The motor is off. Switch reluctance motor, you could go. Actually, it happened to us. For an early prototype, by the way, motors are very reliable. This fault doesn't happen much at all. But for early prototypes, we were at the customer side. They were running that tow tractor in like 18-hour shifts. So you see it's rugged. And we monitor everything remotely. And we saw one of the phases, there is a problem for our inverter, and one of the phases failed. The customer didn't realize it. They kept going. And we sent our engineers overnight with a new inverter. They go and replace it. They told them, and they said, wow, we like that, right? Now, that was an early prototype. It doesn't happen, when you have production. The chance of that is very, very low. But if it happens, our motors, switch lightness motors, are a lot more reliable. These are the things that, again, when the OEM gets over this noise problem that, okay, this is not noisy, a lot of other advantage for this.
So a quick question.
Fascinating information.
Yes. Can you hear me okay, Dustin? Okay. So important, and we can do some follow-up on some articles, Ali, is any published independent production scale performance data where we have torque density, NVH levels, cost per kilowatt, thermal stability, verifying this data. It's very important. So maybe if you could point us to any studies that we could then write about, we can translate that to more common lay person language where business people, finance investors can understand. Make sense?
Absolutely. So we have published a lot of journal papers. These are like peer-reviewed journal papers with external results. The university webpage that we have, electrification.mcmaster.ca, lists all of them. We also have a book titled Switch Reluctance Motors we published a few years ago, and we have a lot of experimental data and a lot of actually benchmarking with permanent magnet versus our motors. We have also the past 2-3 years, we have a lot of, we cannot share those. These are like with OEMs, like, either a two-wheeler, a car, that it's their motor benchmark tested, our motor benchmark tested, acoustic noise, efficiency, torque repels, current, things like that. Those are with those OEM customers, we are not able to share, but we have published a lot of peer-reviewed journal publications.
So that's something that we can look into and, produce some more content on that. So Dustin,
Yeah, thank you.
for sure.
We're running up against our time here at the end of the show, but if we were to fast forward to 2030, another 4 or 5 years from now, how widespread do you think your technology is going to be?
So for two-wheelers, three-wheelers, and micromobility, I believe switch lightness motor is going to dominate that market. And for a lot of industrial vehicles, for automotive traction EVs, my prediction would be 6 years from now, 7 years from now, most likely 15-20% with our motors. And I believe I'm being conservative. If we look at 10 to 15 years, most likely will be over 50%. Because the cost advantage is, that if auto industry and the vehicle industry, we want to electrify. We just don't have enough permanent magnets, and they are too expensive. And the process is not clean, and it's expensive. So there are applications that you cannot remove permanent magnets or rare earth metals. Electric motors is not one of them. The bulk of the electric propulsion motor applications, you can replace them. And it's an engineering science problem. It's not rocket science. Even if it's a rocket science, we do rocket science. Is not impossible. Now, one major challenge Enidime faces is some OEMs have told us that we don't have competition, that they are worried that if they work with us and if we decide, okay, we are not going to supply them, they will be in a difficult situation. So what we need more folks, more investors, more, financial folks to look into this space. There are better ways, or at the minimum, what I'm saying is, don't focus just on permanent magnets and we need to mine and process. Give like 10, 15, 20% on alternatives, right? And that's what we are pushing for.
That's great. I think you just summed up really great what I think decision makers in the industry or even the government should take into consideration when having these conversations of alternatives that are equally as performant as solutions that we're already using. Daniel, any final words?
Yeah, I think that we encourage you, Ali, and your team, because I think this is definitely part of the solution. It may not be the entire solution, but it's definitely part of it. And that's going to mean that you're going to have to establish, for example, what you're doing as a standard that's accepted, that the specifications are designed for, this type of technological breakthrough. So we encourage you to keep pushing forward. That's a big part of what we're about is decentralizing and breaking up the supply chain so that Canada, United States have more stability. We saw during COVID that was not the case. We see it with the rare earth problems. So I think this is part of a broader trend that's extremely important for our health and wealth.
Absolutely. Ali, as we sign off here, if people want to follow Enidime and the work that you guys are doing, or even get in touch about leveraging your motors and their applications, where can they find you? Where can they learn more?
So you can just Google my name, Ali Emadi, and my McMaster University email is emadi@mcmaster.ca, and my Enidime email is ali.emadi@enidime.com. LinkedIn is also a good place. Thank you so much. You are doing a really good service for everyone in the West, and kudos to you. Anybody who wants to advise, support, help, join forces with us. We have very receptive bunch of technical people who are just working, trying to solve a problem, and we need more younger people also to get into the electric motor industry. Thank you so much. I truly appreciate the opportunity you have given me today. Thank you.
Absolutely. Thanks, Ali. And hopefully we'll have you on the show again in the future to get an update on where Enidime is at.
I would love to. Thank you.
Great.